I'm going to actually thank you for the invitation to talk about auroral particle acceleration, which of course is near and dear to my heart. And starting off with this first point, and I'd like to give a shout out to Michelle Thompson, who many of you might know, who gave an AGU talk on planetary magnetospheres a number of years ago. And her first slide was a picture of it, speaking of the artistic impression we had last night, a number of artworks of various styles from classical to abstract, and pointed out that all of those paintings used the same types of paint, the same ingredients, but they were put together in unique and wonderful ways. And she raised that analogy to the different magnetospheres of our different planets. And I think the same thing applies to MI coupling, is that we have the same sort of ingredients, but of course they're all put together somewhat differently at the different planets. I think one of the main points I would like to make is that the paralelectric fields, either quasi-static or broadband, are really the main mechanism, not the only mechanism. There is, for example, acceleration, perpendicular acceleration due to ion cyclotron resonant interactions. But basically, we're going to talk about paralelectric fields this morning. And paralelectric fields, in turn, are generally forming in regions where there's strong field-aligned currents and low densities. And of course, this kind of goes along with what I was talking about yesterday. So let's see if we get everything working here. There we go. So again, I'll start off by talking about the structure of the auroral acceleration region. Of course, many of these will be slides that you've seen before, and then talk about a number of these mechanisms for auroral acceleration, and then finally field line currents. But I'd also point out that really the bulk of the talk will be on these first 2 points about the differences between quasi-static acceleration and broadband acceleration. So we'll go on from that. So I thought I would start with an observation from Earth, which I'm very familiar with. There was a satellite called FAST, which was in a polar orbit with an apogee of about 4,000 kilometers, or about which is about 70% of an Earth radius. And the figure here is sort of a classic passage of FAST through the auroral oval from equatorward to poleward. And it shows this is a particularly nice example because it shows a number of the features that we see in the aurora. First of all, over here we see the, I guess I have it pointed already, these inverted V electrons, the monoenergetic type of electrons that come into play, and which are generally attributed to quasi-static potential drops. Then there's also these alphanic electrons, or so-called alphanic electrons, which tend to occur near the poleward boundaries, but can actually occur all the way through the auroral oval. And of course, these are broadband in energy, very narrowly confined in pitch angle, and in fact are counterstreaming in this particular example, although they're not always counterstreaming. And then another point to be made is that at the same time we see these alphane waves, we see in the ion data, again, a large range of energies, but these peaks in the pitch angle distribution at oblique angles. And those are the signature of perpendicular ion acceleration, or the so-called ion conics, which you may have heard about. So this is the point here. The other thing I should mention here is that, again, as you're all familiar with, if you look at if you make a sheet current assumption with the sheet aligned along a particular latitude, the azimuthal component tells you about the field line current, and the inverted V is in regions of upward current. There's more complicated structure going on in the downward current region. And this red region, you can see the magnetic field kind of bounces up and down. That's a region of no particular sense of field-aligned current, but a lot of filamentary currents. The other thing, and this is my biggest regret about the Juno mission, is that the electric field measurement the electric fields were measured by FAST. And you can see here, in particular, in this alphanic region, there's very strong fluctuations up to a volt per meter in the perpendicular electric field. So this is the sort of things that we understand, sort of the canonical example that gives rise to this sort of a cartoon, where in the upward current region we have these sort of U-shaped potential structures, a lot of wave structures, kilometric radiation, ion cyclotron waves, upward going ions, downward accelerated electrons. Whereas in the downward current region, we see this, I think it was already alluded to, this ion pressure cooker effect where we see strong ion conics, upward electrons again, other wave effects. And then this is supposed to indicate this alphanic region where we have fluctuating electric fields. So this is the sort of story we talk about. And oh well, you know, on this one, I'll go on. Again, a very nice paper by Barry Mock a couple years ago identified these three regions in Jovian aurora, going from equatorward to poleward. There's this diffuse auroral region where we see the broadband electrons over here, and lost cone features. You can see here in the pitch angle distribution, there's depletions near 0 and 180. Then you go into this zone 1, which is mostly an upward current region. The electron downward flux is greater than the upward flux. And you see both inverted V's and broadband type of acceleration here. In this case where you see the inverted V, you also see a strong upward ion signature down here in this region there. And then finally, we get up into this zone 2 region, which is mainly broadband type of distributions, and actually not much going on in the protons in this particular example, at least. So this is sort of the way now we're organizing this. I thought I'd put this one in too. This is something we'll allude to before. This is from a paper by Rob Ebert talking about upward electron acceleration. And the reason I like this one is this shows you the spectrum of the electrons as the satellite passes through, and you get this broadening of the pitch angle distribution. Again, and this is a downward current region where there's upward current. The upward flux of electrons is greater than the downward, and so this is the sort of thing that we expect from broadband acceleration. Okay, so let's see where we have now. So that has led Ale Suleiman and together with Fran Bagenal and Jamie Soleil put together this picture similar to the one, in fact, I think consciously similar to the one from the FAST data. We see this diffuse region, which is also sort of like the alphanic region. There's a lot of alphane waves, although in this case, it tends to be on the equatorward side of the main aurora rather than on the poleward side. Zone 1 is somewhat similar to the upward current region at Earth. We see these strong upward flows, the ion flow upwards. We see alphanic fluctuations, although mainly above the potential structure in this region. They don't seem to show up very much below the potential structure. And then in the zone 2, we also see a lot of counterstreaming particles and some sort of indication of a potential structure, although it's not quite as clear as it is in the case of Earth. I also was sort of charged to talk about the aurora and all the giant planets, but of course there's although there's plenty of data from Hubble of images, the sort of data that Juno is getting in Jupiter's auroral zone we don't really have in Saturn because of the orbit of Cassini, although there were a few passes during the proximal, the final orbits of Cassini before the grand finale. And you see some of the same features as well. Here's upward currents associated with accelerated ions, downward current region, which is a little bit more noisy. And of course, you see also these electron fluxes. So this is my only real slide referring to Saturn. So most of the talk will continue to talk about Juno data. All right, well, moving to the quasi-static parallelectric field, we've talked already about this Knight relationship, which gives a relationship between the total potential drop and the field-aligned current. The one point I wanted to emphasize in this case is that I do not think it's correct to say that the Knight relation is the reason why we have parallel electric fields. When you actually calculate the Knight relation, you assume that there's a potential drop, and you look at the particle trajectories through that potential drop to get the amount of current that's flowing. And in fact, actually, there's a slide that I added last night after the discussion yesterday. This is from this paper by Rolf Bostrom in 2003, where he's assumed a whole variety of distributions, including, well, this is the anisotropic Maxwellian that's in this very nice paper, I should mention, by Friedman and Lemaire in deference to our hosts, which I think, even though Knight always gets all the credit, I think this paper by Friedman and Lemaire is really one of the clearest expositions of the physics behind this. But then they also talk about different, like drifting Maxwellians, kappa distributions. And you can see actually, they never carry these curves up to a saturation regime, but they all end up having a saturation regime as well, just like in the night relationship. So this is the type of distributions that we get. So again, it's not just purely for Maxwellian distributions. Now, another thing I would like to call out is this very nice paper by Alicia Ray in 2009, pointing out that this, what she called the current choke model. And the idea is, I drew these sort of potentials for the polar cap before, but this is for downward going electrons. And again, we have this effective potential, that's the electrostatic potential plus mu b. So it's a potential that depends on the magnetic moment of the particles. And because of the mirror forces, there's this barrier. And again, none of the particles, only the particles that are above that barrier can come down and precipitate. In fact, the ones that are in the dashed lines here are the ones that actually are reflected before they get to the ionosphere. The ones in the solid lines then would be the one that contribute to the field-aligned current. And of course, what this does is it limits where this peak should be. And let me go to the next slide to talk about, oops, I'm going to jump this, I'll come back to that one. But this peak tends to happen in this place where the density is very low. And this is also a picture from Leish's paper showing results of a Vlasov simulation that actually considers self-consistently where these parallel potential drops happen. And so, this is happening not way out in the plasma sheet, but in this particular case, at lower latitudes, it's around 2 or 3 Jovian radii. So let me go back. I did these in a little bit wrong order. Here's sort of our model of why parallel fields do occur. And this is a lot of work that I've done with Jens Song over the years. And in our opinion, the starting point is the large magnetic shear that's basically caused by vorticity in the plasma flow. And that vorticity is where there's a variety of things. I mean, in the Earth, in the large scale current systems, that's largely the solar wind interaction. At Jupiter, as we've talked about before, there's co-rotation and the breakdown of co-rotation in the outer magnetosphere. Of course, those can break up into turbulence interactions, which I won't say much more about because Joachim Sauer will tell us all about that tomorrow. And of course, the other place where you can induce vorticity in the flow is when the moons Io and Ganymede and Europa pass through the co-rotating plasma of Jupiter. And the idea here is that if you start with the curl, with the B being, with the magnetic shear, if you will, the particles need to catch up in some ways to balance Ampere's law. And the role of this displacement current term, which we usually don't worry about in MHD, but it has to be there in order to increase this parallel potential, parallel electric field, which then accelerates, in this case, the electrons, and then that ends up carrying the current. So this whole chain of events is where we end up with parallel electric fields. And then when the current exceeds the critical value, then various kinetic effects, in particular the formation of plasma double layers, can provide the quasi-static electric field. And so coming back to this slide, where does that form? Well, the drift velocity of the electrons that are carrying current, the velocity of the electrons with respect to the ions, is the current divided by the density and the charge. And as we consider a flux tube coming towards the planet, the ratio of the parallel current density to the magnetic field stays constant. And that means that this drift velocity scales at B over N. So I always want to emphasize this ratio of B over N. The location of the parallel electric field is where B over N is large. And so if you know what the altitude distribution is along the field line, as in this picture from Leish's paper, then you can find where the parallel electric fields will form. And in fact, in this model, there's actually 2 double layers that form in this particular case. And so this is the point here of this story here is that the source region, again, for the night type relation is at this choke point, as we call it. Well, if B over N matters, that means that the parallel electric field is going to be in places where the density is low. And so what is the density along a Auroral flux tube? Well, here's one study by Sadie Elliott where she looked at a variety of different cases, and you can see the color coding goes from the blue is less than 1 particle per cc up to higher energies. These data are primarily taken in the region between the main auroral oval and the Io footprint, and so these are relatively high. But more recently, Allegrini et al., this Jade team, has looked at this picture and shown that the density falls off very quickly, and that's consistent with results from Ali Silliman about the wave data, which shows you once you start getting into this zone 1, the density starts to get down to values of 10 to the minus 2. So we do indeed have very low densities in this region where the parallel electric fields would be forming. So this is the nice cases. So why does that happen? And one of the main mechanisms, which I think is relevant here as well, was actually one that was illustrated very nicely by Chris Chaston in the context of Earth, where they had a fast flyby where it passed through a deep density trough, and near in this region was a very alphanic region, very strong alphane wave turbulence and upward flowing ions. And in addition to accelerating electrons parallel to the field, the kinetic alphane wave can accelerate ions perpendicular to the field. And those ions, having an increased magnetic moment, feel an enhanced mirror force up the field line. And of course, this whole process is sort of self-sustaining, because when you get these gradients, then you have this so-called phase mixing process that takes place, which makes the perpendicular wavelength of the waves smaller, and as I'll mention in a moment, that's important for the particle acceleration. We also have some nice work from Barry showing that there are these upward ions. If we see this nice inverted V type of region, this is this nice example where the inverted V kind of breaks up near the peak and becomes more broadband. And in the regions where we have the inverted V, we have this larger ion outflow. And in this region here, this example isn't particularly good, but you can see a little bit of an enhancement here at an oblique pitch angle. And so I would tend to interpret this as being a region where we have either alphanic or perhaps Whistler mode turbulence that's causing scattering these particles into a broadband distribution. And either of those wave modes can accelerate ions perpendicular to the field and produce these ion conic distributions. So this whole type of picture seems consistent with what Chris Chaston and the FAST team have discussed at Earth. And of course, the other point, as I mentioned yesterday, is that in regions of downward current, and thank you, this is the ambipolar field can keep the densities low. So I have 2 minutes to talk about alphane waves. That's exciting. So here's some measurements from Gershman et al. From the MAG team, looking at this nice distribution of electrons in sort of the 1/10 to 1 Hertz range, and with nice power law distribution. And Ali has done this study where we have, this is actually a different event, but you also see this spectrum from MAG, and then it really looks like it continues on into the waves regime. And in fact, you see some structure here near the ion cyclotron frequency. And so this does seem to be a rather broad spectrum that comes into play. And what I'd like to mention is this idea that of the ionospheric alphane resonator, that the alphane speed jumps up, in Jupiter's case, to nearly the speed of light, or to basically the speed of light. And this sharp gradient can reflect waves, and we get these peaks. Now, the first thing you notice is that the observed spectrum was broadband, but remember that Juno is passing through the auroral zone at a relatively large rate of speed. I've estimated, just based on some of the pictures, about 20 kilometers a second. I'm willing to be corrected on that. If we're down at the electron inertial scale, which for one particle per cubic centimeter is 5 kilometers, that's 4 hertz of Doppler shift. So that's really going to smear out these spectra and produce a broadband distribution. So again, here's the dispersion relations for kinetic alphane waves. Again, the relevant scale length in most of the auroral acceleration region is this electron inertial scale. Actually, Joachim did a very nice study a few years ago quantifying this and showing that throughout a lot of the flux tube, until you really get out into the plasma sheet, you have the inertial regime is the more important than this more kinetic regime. And so this gives us this small scale then means that we need narrow perpendicular structures, or we need filamented currents, and we also need rapid time scales, and those are the ones that can be produced by this by this resonator. And this is, I guess I'll, in interest of time, you can look at, these are just computations of the full kinetic dispersion relation, including the damping rate and the E over B ratios, which again are a really nice way of identifying alphane waves, kinetic alphane waves, if you have electric field data. So anyway, let's think about a little bit more about the field aligned currents. Of course, we have this large scale current system that we all know. And as a nice paper by Kotsiaris a few years ago pointed out, that this is actually, his model was fit better with a more filamented current structure. So we do have this process of the large scale current system really having a lot of embedded small scale currents, something we also see at Earth actually. And that can be produced in a number of different ways. Here's a picture actually that Aaron West showed yesterday from one of our simulations, which is a nice picture of this phase mixing where the alphane speed is on a gradient where it goes faster one side than the other and makes these shears. You can also get this sort of structuring due to the real source, due to turbulence and the sort of stuff that Joachim will talk about tomorrow. The other suggestion that I think is maybe a little bit crazy, but interesting, just gives me an excuse to show this nice JunoCam picture of the turbulence in the atmosphere. Could some of that couple to the ionosphere? That would be interesting. So I'd like to just mention a couple of things about the moon plasma interaction. Jamie's going to talk about this in Thursday, but I thought I'd advertise a little bit, actually, some stuff that I had at a poster in the virtual MOP last year. Basically treating Io as a cloud of Pedersen conductivity, and Stefan Schlegel will talk about effective Hall currents in this regime. But we've developed a computer model of this. Here's Io trucking along and producing these alphane waves that go back and forth, bouncing off the ionosphere. And the point of this slide too is that the spacing of these spots is going to tell us about the density profile. So if we really start to understand that, we could use that as a diagnostic of the plasma. The other thing that we noted in this is that if you look at the different ionospheric conductivities at Jupiter's ionosphere, not in Io, there's a lot of structure depending on whether this conductivity is low or high. In this case, 0.1 or 10 MOS. And the thing that's interesting about this is that in this low conductivity case, or low conductance case, the current pattern actually, because of the reflection coefficient of alphane waves, actually alternates like this. And it's very tempting to associate this with the sort of zigzag type of auroral structures that are seen by the GIRAM instrument on Juno. So this is the sort of one explanation for this. And as Schlegel will talk about, I forget if it's today or tomorrow, then this also seems to come about by putting in Hall effects at Io. So that's kind of the story about that. So that's what I basically have to say. Again, Jupiter's aurora has a lot of these same elements that we're familiar with from Earth. As we all know, broadband acceleration seems to be more common. And of course, one of the big differences is at Earth, the downward current region is largely dark, sometimes called the black aurora, rather dramatically. But of course, because of this, a lot of broadband acceleration, we still see aurora in the downward current region. And my point is that alphane waves in this trapped in this resonator provide a natural mechanism for this broadband acceleration. There is also some discussion about whether Whistler mode waves can do the same thing, which is certainly possible. Although in my point of view, the Whistler mode really has to be generated by an electron beam itself. So you sort of have a chicken and egg problem of whether the electrons come first or the Whistlers come first. And so this is a subject that can be a subject of future debate. And of course, looking at Io is something that we all love to do, and we'll do some more work on that. And I'm sure that we'll hear a lot more about that the rest of this week. So that's what I have to say. Thank you very much.